Hi, my name is Biv Wadden, and I'm a PGA teaching professional in the western suburbs of Chicago. This morning, I'm here in my putting instruction studio, and I want to deliver a short talk on optimal acceleration for David Orr and his Flat Stick Academy members. Why is optimal acceleration important, and how do we go about achieving it? Okay. So key takeaways from today's video. First, we're going to learn about Dr. Robert Grober's theory of optimal acceleration, rhythm ratios, and stroke times. We're then going to learn about the statistical advantage that makes proper acceleration the key to distance control. This video is really all about distance control and how to achieve it properly. I'm going to talk about what I consider to be the pathologies of poor acceleration and how to identify them. And then finally, we're going to conclude with a case study on how poor acceleration was fixed, and fixed rather quickly. Okay. So Robert Grober is a kind of a rare combination. He is a Yale PhD physicist in the Department of Applied Physics at Yale. And he's also a mid-single digit handicap golfer. And so he's done some very detailed and excellent work on both kind of optimal force applications in the putting stroke, so acceleration, stroke times, rhythm ratios. He's also done a lot of work on green reading and break margin models. And actually most recently did a paper on the alpha controversy that some of you may follow between Michael Jacobs and Sasha McKenzie. Anyway, he authored this paper, Resonance in Putting, in the early 2000s. And this was a seminal paper. He really cracked the code for the rest of the industry on the importance of stroke times, the ratio of backstroke times to downstroke times, and acceleration. And before he came along and wrote this paper, we really didn't know how important this was. Okay. Now, the paper is complicated, and I want you to know you can see some complicated formulas up there. I'm saving everyone from having to wade through the paper. I've done it, I've modeled all this, but it's intense. And what I want to do is give you the plain English version of this today. Grober starts out by saying that world-class putters have putting strokes that are similar to a pendulum driven at twice its natural resonant frequency. So what does that mean? Okay, I want you to imagine here's a little girl on a swing, okay, and the putter head is the little girl, okay, and what she's doing at both ends of the swing is there's a little bit of a force couple. She gets to the back end of the swing, and she pulls in the rope and then kicks her legs forward. And then she gets all the way to the forward end and she pushes the rope and kicks her legs back the other way. Okay, so she's applying a very small force at both ends of the swing to kind of preserve the rhythm and the amplitude of the swing that she's going through. Okay, and so this is the forces that she's putting in with her little girl leg kick, okay, are what's establishing that natural resonant frequency, okay? Now, the putting stroke is different, okay, and here's how it's different. We don't hit a putt like starting in motion and then moving, back through impact to hit it, okay? We're actually starting a putt from a dead stop. And we have to create enough cumulative takeaway forces, and then after that, create two sets of transition forces. The first force to slow the putter head down so it comes to a stop, and then we need to keep those forces going back in the direction towards the target so that we can get the putter head through the ball and all the way to our finish. So when we do that, if you take a look at Tiger on the left here, in Grober's theoretical optimal world, the backswing length of time would be 2/3 of a second, 0.67 seconds. Okay, and So this little piece of the pie is 2/3 of a second, and then there's the rest of the pie going from the end of the backswing all the way through to the finish, okay? That's also 0.67 seconds. Those two match up. And when we match those two up, the downstroke time ends up being 1/2 of that, 0.33 seconds. And then from impact to finish, we have another 0.33 second increment, okay? And everything, fits nice and neatly in there, okay? Now, Grober goes on to say that these cumulative takeaway forces, okay, there's the putter being brought away from the start, okay, they need to match the cumulative transition forces. So, like I said earlier, the cumulative, the first piece of the transition forces is to slow the putter down before it gets to the end of the backstroke. And then we got to keep the forces going back in that direction so that we can return the putter head through the ball all the way through impact to the end of the putter swing. Okay? So when the cumulative takeaway forces equal the cumulative transition forces, okay, that's a requirement that Grober put into this overall equation, okay? Now the last piece in this is getting the putter head to arrive at the ball with constant velocity, which said another way is zero acceleration at impact, okay? So this is a graph I put together from Grober's model, and the blue curve is the velocity profile, the gray curve is the acceleration profile, okay? And you can see at impact, okay, that vertical line at impact, the velocity profile, it's reached a maximum, okay? And it's not going up anymore, it's not going down yet, okay? It's reached a maximum and that velocity at impact is constant. You only get there when the acceleration has managed its way all the way down to zero. Okay, so zero acceleration is constant velocity. Okay. So here's the punchline from Grober. Now, I've kind of summarized the 4 key aspects that we just reviewed of his theoretical model. And he says that when these characteristics are achieved, okay, speed errors at impact are statistically minimized. This is an important key to distance control. Okay? So let's look at this statistical argument, and we're first going to take a look at the real statistical argument, and then there's an easier, more intuitive way to look at it. But if you remember from college statistics, the variance, which is I've shown here as classic sigma squared. The variance is equal to the sum of the speed errors relative to like our intended speed that we meant to hit the putt. Okay, but Grober in his paper proved that the overall variance was multiplied by another term, and this term basically is the either balance or imbalance of the cumulative takeaway forces and those cumulative transition forces. When the two are matched and balanced, this term on the right is its smallest, it's minimized, so that when we do a good job of matching the takeaway and transition forces, the overall speed errors that we get are at their smallest. Now here's a more intuitive way to look at this, okay? Here's our velocity curve. Okay, and I want you to consider 2 possibilities, okay? The first possibility is we're going to hit the ball while the velocity curve is rising, okay? And I want you to imagine, you can see how steeply sloped that velocity curve is. So if the putter head gets to the ball a little bit too early or a little bit too late, okay, we're going to have a very different speed result, okay, in terms of the ball speed off the putter head. Okay. Now, let's imagine the alternative where we're going to hit the putt at the top part of this curve where there's constant velocity, okay, and now if the putter head gets to the ball a little bit early or a little bit late, it doesn't matter. We're basically you know, we've got a constant velocity of the putter head, and we're not going to have very different speeds, ball speeds coming off that face when the putter head is arriving a little bit early or a little bit late, okay? Now here's what this looks like in the real world. This is a SAM Putt Lab graph, and the graph down below is the acceleration profile. The graph up above is the speed profile, okay? So notice in this putt, this is a correctly hit putt, and notice how at impact, and the impact is denoted by this kind of vertical hashed line. Notice how the acceleration is coming right down through the zero line, right at impact, okay? And then look at the result in the velocity curve, okay? And it always strikes me how flat that curve is before impact when you do this right, okay? It's very, very flat, and it's flat for, you know, it's a constant velocity for 1.5 inches to 2 inches of the putter head, you know, behind the ball. So this is really what we want to achieve. Now, this is what it looks like when there's remaining positive acceleration. So here, impact is happening with quite a large amount of positive acceleration. And look at the slope that is there at impact and the speed curve. That speed curve's going up, there's a collision, and interestingly, the speed of the putter wants to go back up again, you know, post-collision. That's how much positive acceleration, how much force is going through that putter head into the ball, okay? Okay. Now, quite often, like in the instruction community, there's a question, can acceleration really be taught? Can it be learned? I strongly believe it can, and I've been very successful across many, many students very quickly teaching proper acceleration. Now, we're going to talk about the do's and don'ts of this, and here is, so we're going to start off with the don'ts. The first ones should be obvious. We don't want to intentionally accelerate through impact, and everyone, you know, who's been around for a while has heard the mantra of, son, you know, just make sure you accelerate through impact, okay? And, you know, Grober proved that that is a bad, bad, bad idea, okay? The most obvious kind of physical manifestation of positive acceleration and impact is when there's a takeaway and you see, and it's relatively short, and then the putter just pushes the grip through impact, and you see a short follow through with a very long, a short backswing with a very long follow through, okay? When you see that, you know the acceleration profile is way off, okay? The next one is when the backswing time is too slow, and so you're really not developing those cumulative takeaway forces. They're just not enough, and then you get a mismatch. You finally build up your transition forces, and there's a mismatch between the two, okay? And that mismatch, you know, it's slow here, and then boom, you get the long follow through again, you know, in that case. Third, locking down the wrists, okay? Remember that little girl leg kick, okay? If the wrists are locked down, we don't have any, you know, the rhythm and the little girl leg kick coming from the slight bend in the elbows and the wrists, okay? You need a little bit of that in the swing. So if you ever get a Hackmotion device, you know, put on your wrists, 3 to 4 degrees of movement is typically what I see out of wrist movement, out of good putters, okay? Not 0. And not 7, 8, 9, or 10 degrees either, okay? But, you know, anywhere from 2 to 4 degrees on both sides, the takeaway side and the release side, okay? Don't suffer with a bad putter fit. Too heavy, too fat, too short. If a putter gets too heavy, you just, you know, you've got to get the putter away from the ball, you got to transition it back. Too much weight makes it humanly difficult to manage those forces and balance them out. I like to see the static weight of the putter pretty much be between 510 and 540 grams, okay, 545 maybe, okay. You get above that, you're going to have problems. You get below that, you're going to have, you know, problems. Although below that is better than above. And then too fat. A lot of people put the fat super stroke grips on, and they're really trying to lock down their wrists with those grips. Okay? And that's really not a good idea. All right, so let's look at some of the do's here. We do want to keep the follow-through length equal to or shorter than the backswing length. Okay, so when you see that, okay, we take it back, okay, we transition, we let the putter head kind of flow freely into the ball. Then there's a collision. That collision takes the energy out of the putter head, and the putter head should kind of naturally slow to a length that if you've achieved zero acceleration and impact, that length usually is about the same length as the backswing. Okay, it really does help to very lightly break the putter head post impact. You know, to kind of like just, you know, slow it down on purpose, and that slowing down of the putter head. Your mind's going to anticipate that kind of pre-impact, and that's one of the things that kind of helps take the acceleration kind of air out of the balloon. Okay? And then, of course, we've got to allow for a micro amount of wrist movement in the transition. So, you know, it really starts up top with the shoulders and the elbows. Okay, and then as we transition back to the ball, okay, this all kind of like lags behind. There's a little torque on the elbows and wrists, and then then this slows back down and it releases and everything catches up. Okay, now let's listen to Tiger Woods back in the day when Butch was teaching him about a tip that he got from Ben Crenshaw.
The key was that it just gave you a much better feel.
I could feel the weight of the putter head. I remember in '97, when I made a run at Mark at Pebble Beach, we were talking to Ben Crenshaw, picking his brain on the practice tee. Just picking his brain on how he likes to feel the putter. And he's always telling me, you know, he's like this, you can just see it falling in his hands real light. He says, I've always believed in letting the putter head get behind my hands. And then from there, let the weight of the putter head hit the golf ball. Well, I said, okay, that makes sense. I took it back there and my hands were going like this. I said, my hands are too tight. And so, you know, I remember him just holding the blade like this. I had to loosen up my hands, get my putter head behind my hands, and from there, let the weight of the putter hit the ball. I ended up shooting 63, 64 in the weekend, putting that way after a little lesson from Crenshaw.
So there you have it from Tiger. Okay, you need a little flow. Okay, so before we get into the case study, I want to explain a little bit about how the Capto acceleration curve works. Capto is this device that goes on the shaft. Many of the flat stick members are used to David talking about this putting analytic device. This is one of the from my opinion, key graphs in the whole Capto system. And if you focus on the lime green sine wave, okay, that really represents first the cumulative takeaway forces. The area under the curve of that lime green sine wave are the cumulative takeaway forces. And then, by the way, the yellow vertical line is the end of the backswing. On the far right, there's an orange vertical line that is impact, okay? And the cumulative transition forces are kind of equal and opposite to the cumulative takeaway forces. And it's depicted, it's very visually depicted on this graph. And by the way, notice how the cumulative transition forces actually start before the end of the backswing, before the vertical yellow line, okay? Now, the yellow and blue squiggly line is the actual force production relative to the lime green ideal. And when the shape of the actual ends up along that same sine wave, you know you're doing it right, okay? So here's our case study. And this is a low handicap, one of the top senior amateurs in Illinois, happens to be a good friend of mine. And he came to me and, you know, he's a good putter, but he was, because he's a good player overall, was always looking to see if there was any issues. And he did have a very slow takeaway, and his acceleration profile was actually way off. And he, at one point, became kind of mesmerized by trying to release the toe like he heard, you know, Tiger was always trying to do. And he actually started, like, kind of flipping his wrists through the impact to release his toe. And so the combination of the slow takeaway, you can see the force production pre the end of the backswing is way under the lime green, you know, sine wave, and then very late in the stroke, you see that wrist throw, and boom, the acceleration, quantity of acceleration is way great. It did not manage its way back down to zero. Okay, so how did we fix this? Okay, the first thing I asked him to do was to speed up the backswing. Okay, he had to get started a little bit faster. His backstroke time was 0.7 seconds. Now that may sound very close to the 0.67 seconds that, you know, Grober's optimal backstroke time is. In a subsequent video to this, I'm going to talk about how the real world does deviate from some of Grober's theoretical optimals. Okay, and this is our first example of this. Most of the time in the real world, the backswing, the stroke length, the stroke time, total stroke time is not going to be 1 second. It's going to be, you know, maybe 0.85 seconds, and that's going to split between kind of, you know, 0.6 seconds and 0.3 to get a 2-to-1 ratio. Okay, so anyway, he's at 0.7, and his follow through is longer than his backswing. Okay, so his backswing is basically 9 inches. His follow through is 12 inches for a total of 21 inches of putter travel. Okay. Now he took, I don't know, he maybe took 50 strokes or so in 45 minutes, and those were the results from his initial 10 strokes. His final 10 strokes, okay, we got his backswing time shortened from 0.7 to 0.53. And then I also kind of asked him to basically stop the putter head also. And you can see that the symmetry between the backstroke length and the follow through improved. The total travel from end of backswing to end of follow through was only 16 inches, and he cut 5 inches off of his total travel from end of backswing to end of follow through. Okay. Now there was a second solution in this that was also very important, and that was creating better, what I call, you know, wrist movement symmetry. I asked him, when he was going back faster, to also move his hands back to the target sooner than he would otherwise. So you can see what's happening to the torque in my wrists when I get back here and get it going back to the target sooner. And I put a Hackmotion device on his wrists, and initially when he was taking it back, suppressing his wrist movement and releasing the putter head, he had 1 degree of wrist extension loss on the backswing, and then 6 degrees of extension gain on the follow through. So 1, 6. When I simply just, you know, and this is like the little girl leg kick, okay? It's a very small, little, nuanced thing. But when I asked him to just kind of transition back to the putter sooner, and, you know, it doesn't have to be with the hands. It can really be, you know, with the shoulders, you know, up here. You just kind of reverse the rotation earlier. He got much better symmetry in his wrist movement, okay? He ended up with kind of 3 degrees of extension loss on his backswing and 4 degrees of extension gain on his follow through. And I typically see this out of successful good putters where there's really kind of like a 1 degree net extension gain pre-impact. So this went from unorthodox to very orthodox. So if you look at the top force profile, we saw that already, but look at the improvement in the second bottom acceleration profile, okay? You can see how the movement of the kind of yellow and blue actual lines mirrored the shape of the sine wave much better, okay? And this was done, it says 45 strokes over 48 minutes. And you know, he was doing it beautifully and consistently, no problem. But he just needed a little help on how to go about doing this. Capto is a wonderful device for providing feedback on this very issue. Okay, so there you have it. Optimal acceleration in the putting stroke, how to achieve it, how to know when it's not right. I encourage everyone to, if you can, make the trip down to Pinehurst to see David Orr. If you happen to be in the Chicago area and you can't get down to see David, my contact information's on this slide, and think about coming to see me. Thanks everybody for listening, and there's going to be a subsequent video about the real-world departure from some of this theory as it relates to stroke times and rhythm ratios. Thanks for listening.